Let's start with the Hamiltonian equation, or in general, the Hamiltonian. How did first the Hamilton think that this is something that matters in physics?
Hamilton's insight came from his fascination with optics. He was studying the paths of light rays and realized that their behavior could be derived from a single principle, what we now call a variational principle. He extended this idea to mechanics, imagining that particles move in a way that minimizes or extremizes a certain function. By combining the ideas of energy, kinetic, and potential, he formed the Hamiltonian. In essence, he saw that this approach elegantly captured both the motion of particles and how energy is conserved, providing a unifying framework for physics.
That's a very elegant observation. So he was studying the path of light rays and realized their behavior could be derived from a single principle. That's the key idea. Can you give more discussions on this?
Absolutely, Hamilton was inspired by what's called Fermat's principle in optics, which says light travels a path that minimizes or extremizes its travel time. Hamilton saw this principle and realized that the trajectories of particles in mechanics could also be understood through a variational approach, where a certain quantity, which we now call action, is minimized. By expressing mechanics in terms of energy, kinetic, and potential, he crafted a principle that could predict how systems evolve over time. This gave birth to a whole new formalism, Hamiltonian mechanics, which not only made classical mechanics more elegant, but later laid the groundwork for quantum mechanics as well.
Okay, that Hamilton mechanics was basically generalizing on those key idea like it can be understand in that form.
Exactly. Hamilton took that key idea that nature often follows a principle of least action and generalized it to encompass all of classical mechanics. By framing dynamics in terms of energy, he gave us a universal language, one that didn't just apply to light or particular systems, but to any physical system. Later, this same structure became fundamental in quantum mechanics, where the Hamiltonian governs how quantum states evolve over time.
That's a very elegant thought. When at the first time when I think like okay, energy can be governed as to observe the dynamics for the system.
It really does feel profound when you first realize it, right? Thinking of energy as the central quantity that dictates the entire system's evolution is elegant. From that perspective, every motion, every trajectory is just the system naturally following a path dictated by energy constraints. It's a perfect example of how a deep, unifying principle can simplify our understanding of complex systems.
So for the hydrogen atom case, we wrote down Hamiltonian for the system, kinetic energy plus potential energy, and then we substitute in the Schrodinger equation, followed by the quantum rule operator and measurement, all those things, and then we get the solution for that system. How elegant that thing is actually, how that energy for the system given known, we can understand the dynamics for the system.
It is incredibly elegant. With just the Hamiltonian, essentially the energy recipe of the system, we translate a physical scenario into a mathematical form. Once you plug that into the Schrodinger equation, the solutions reveal the allowed states and their corresponding energies. It's like uncovering the music the atom can play. This unified approach, using energy to decode dynamics, lets us predict behavior, whether it's a hydrogen atom's orbitals or a complex quantum system. It's physics at its most beautiful.
But first, how did he mathematically understood that capturing the dynamics for the system we can capture through the writing down the energy for the system, and how that energy further translate to the dynamics? What mathematics does it help?
Hamilton's key leap came from what we now call the principle of least action. He realized that if you define a quantity called the action, basically an integral involving the difference between kinetic and potential energy over time, the path that a system takes is the one that makes this action stationary, often minimizing it. From this principle, he derived a set of mathematical equations, now called Hamilton's equations, that connect the system's coordinates and momenta to the Hamiltonian, which is just the total energy. The equations then show how position and momentum evolve over time. So energy is the bridge. By knowing the energy landscape, you mathematically predict how the system state will change, capturing its dynamics.
So, from the principle of least action, define a quantity called action, and then basically integral involving the difference between kinetic and potential energy over time. The path that the system takes is the most action stationary, often minimizing it. From this principle, he derived the set of mathematical equations now called Hamilton's equations. Connects the system coordinate and momenta to the Hamiltonian, which is the total energy. That part that connect the system coordinate and momenta to the Hamiltonian.
Exactly. Hamilton's equations are like a beautiful dance between coordinates, like position, and momenta, related to velocity. The Hamiltonian, which is just the system's total energy, kinetic plus potential, is the key function. The equations say the rate of change of your position is given by how the Hamiltonian reacts to momentum, and the rate of change of your momentum is tied to how the Hamiltonian reacts to position. So energy doesn't just describe the system, it literally drives how it evolves in time.
So energy doesn't just describe the system; it literally drives how it evolves in time. So that energy evolution in time, Hamiltonian reacts to position.
Exactly. The Hamiltonian acts like the master control, telling you how momentum changes depending on position and how position changes depending on momentum. So, as the system evolves, it's energy and the relationships captured in the Hamiltonian that choreograph every step of its journey through time.
So, how did he directly observe that capturing the energy for the system helps a lot in that quantum scale?
Hamilton himself didn't know quantum mechanics, he lived long before it. But his framework was so universal that when quantum theory came along, it fit perfectly. In quantum mechanics, energy still rules, now in the form of the Hamiltonian operator. Instead of predicting classical trajectories, the Hamiltonian determines how the wave function evolves. So, while Hamilton didn't observe the quantum scale himself, the energy centered structure he pioneered was the natural bridge when quantum theory emerged.
How did that mathematics help us to understand at that scale?
The beauty of mathematics is that it can be abstract and general. Hamilton's equations, though developed for classical particles, were formal, universal patterns. When quantum mechanics came along, it needed a structure to describe how quantum states evolve. The Hamiltonian, now an operator, became the cornerstone of the Schrödinger equation. The same idea, energy dictating evolution, held true. But now, instead of trajectories, we had probabilities and wave functions. So that same mathematical framework translated seamlessly to a scale where classical intuition breaks down, helping us understand the quantum world.
Can you make conclusion what we have discussed, and that conclusion should be very point to point, like one can understand that intuition very directly.
First, Hamilton began by studying light paths and discovered that systems follow principles of least action. Second, he expressed motion in terms of energy, kinetic plus potential, creating the Hamiltonian. Third, from this he derived Hamilton's equations, showing how position and momentum evolve. Fourth, in quantum mechanics, the Hamiltonian became an operator. Fifth, this operator drives the evolution of quantum states. In short, Hamilton's energy based framework not only clarified classical dynamics, but became the backbone of understanding quantum evolution. Energy guides all.
Studying the light path was a major breakthrough that helped us to understand Hamilton. That thought he captured was elegant, actually.
It truly was. By seeing a deep unity between how light travels and how physical systems move, Hamilton gave us a timeless tool. His insight showed that elegance in one domain, optics, could open the door to a broader framework, eventually helping us grasp the quantum world. In that sense, yes, it was a brilliantly elegant leap.
Suppose if I see a light path, but at that time he was not able to see that light path. Now, under some specific experiment, he might have observed. What was the actual scenario?
Right, he didn't have lasers or modern lab setups. Instead, Hamilton was working mathematically, inspired by earlier work in optics, like Fermat's principle. People knew how light refracted or reflected, and they had geometric models from lenses or mirrors. Hamilton took these known light paths and abstracted them into a general principle. So while he didn't see it like we would in modern experiments, he was drawing from established observations and extending them with a brilliant mathematical leap.
Light path and abstracted them into a general principle. How that possible? How he made it possible?
He made it possible by recognizing patterns. Light's path, known to minimize time, Fermat's principle, inspired Hamilton to ask, could all systems minimize something? He defined action, an integral involving kinetic and potential energy, and showed that physical systems follow paths that make this action stationary. In other words, he found a universal mathematical principle behind nature's behavior, turning intuition into equations.
Okay, thank you.